Our feature presenter for this event is Bill Gatheridge, Product Manager at Yokogawa. Bill is responsible for the Power Analyzer product line as well as other measuring instruments. He has over 20 years' experience with Yokogawa in the area of precision electrical power measurement. Bill has been running both live and WebEx seminars on various power measurement topics and applications for the past 10 years. He is a member and vice chairman of the ASME TTC 19.6 Committee on Electrical Power Measurements for Utility Power Plant Performance Testing. He is also a member of the RTCA-DO-160 Committee for the Aircraft Power Testing and has worked with an ASHRAE Committee on Variable Speed Drive Testing. Bill has a degree in electrical engineering from Purdue University. Without further ado, I would like to hand it over to Bill.
Thank you, Sophia, and hello, everyone. Thank you for joining our webinar today on electric motor testing. We got a lot of good information for you, and we're going to fill up this 1 hour with hopefully a lot of information that will help you in your work and the things that you're doing. A little bit about Yokogawa. It was founded in 1915 based on electrical meters. They made the first electrical meters in Japan, the moving coil type, and so Yokogawa's history is well established in the electrical measurement. The North American operation started in 1957, and right now worldwide our sales are in excess of $4.3 billion. So we have a very large corporation with a lot of resources behind us. We have 84 companies worldwide and over 19,000 employees operating in 33 countries. And this little meter showing up here is a pretty classic meter with the wood case, the moving coil with the mirrored scale and the pointer. Compared to the instruments that we're using now, these very sophisticated, high technology digitizing instruments that we need to make the measurements in the type of power electronics that we're using today. Today, we're going to give you a 3-step process for a complete electrical test of your AC motor and your variable speed drive system. We're going to start with a review of basic electrical power measurements, review of mechanical power measurements, and then instrument considerations that you need to think about for these types of applications, along with a review of some of the current sensors required in these applications. Then we'll talk about the 3-phase AC motor measurements, particularly on a 3-phase 3-wire system. And we'll look at the mechanical power measurements, speed and torque sensors, and the motor efficiency measurements. Next, we'll look at the variable speed drive, the PWM pulse-width modulator type drive, look at the input and output electrical measurements of the drive, look at the how to measure drive loss and the drive efficiency, and some other typical drive measurements. We'll cover some of those. And we'll kind of put it all together for you. Look at the motor system, the drive system, and the total system measurements and efficiency, and touch a little bit on the IEEE Standard 112 for motor testing here in North America. Hopefully we'll answer your questions as we go along, and as Sophia said, if you do have a question, please submit those, and we will answer them either at the end or by email. So starting off, we're going to review our basic electrical power measurements. We'll start off, well, what's a watt? Well, in the DC source, it's very simple, as the volts times the amps. In the AC source, it's the volts times the amps times the power factor. Now, you'll note that I say power factor, not the cosine of the angle between voltage and current or cosine of theta. So it is power factor that we want to look at. So how do we measure power in these instruments that we have now? Well, in the Yokogawa digital power analyzers, we digitize the incoming voltage and the incoming current. So these are used by high-resolution digitizers, ADD converters, high speed, and we take instantaneous values of the voltage and the current, and we multiply and accumulate those over some time period and then integrate them over that time and multiply by 1/T. So it's the instantaneous voltage multiplied by the instantaneous current and then integrated over a time period. And in our instruments, that time period is typically some portion of what we call the measurement period or the update rate. So the true RMS measurements, this is the power calculation that we just showed you. The RMS values are similar in that we take the digitized values of the voltage or the digitized values of current, and this is an RMS, so it's a root mean squared calculation. So these calculation methods provide a true power measurement. Okay, that's a true power measurement, and it's a true RMS measurement, and it's on any type of a waveform. Okay, it does not have to be a sine wave, any type of a waveform, distorted or whatever, and it will include all the harmonic content up to the bandwidth of the instrument. So these are true power measurements and true RMS measurements that we're making in the power analyzers today. Then power is calculated basically as the sum of all of the harmonic contents that are available in whatever type of waveform that you're looking at. So we look at the DC component plus the first order. This is what this is called, the first order, the D1 times the I1 times the cosine of theta 1. So the phase angle between the fundamental voltage and current, and so on. So we sum all of those together. That's basically how it's being calculated, or more precisely, it's the summation from the minimum order to the maximum order of all of the harmonic components in the system. On making power measurements, we base this on Blondell's transformation. Blondell went through all the math and the vector analysis to prove this, and so his theory stated that to measure total power, okay, we measure total power with one less wattmeter than the number of wires. So if we start with a single phase 2-wire measurement, we're going to use 1 wattmeter. So we'll make 1 voltage measurement and 1 current measurement. Now, if we use a single phase 3-wire, this would be in North America like our split phase, we call it, for major appliances and things like that, where we have line 1, line 2, and the neutral. Okay, we've got 3 wires. We're going to use the 2-wattmeter method. And then on the traditional 3-phase 3-wire, again, we got 3 wires, so we're going to use the 2-wattmeter method. We're going to measure 2 voltages and 2 currents, and then internally inside the wattmeter, that will be totalized to give you the total 3-phase power. Now, on a 3-phase 4-wire system, when you have the 3 phases, your 4th wire is a neutral. Voltages are measured line to neutral, and we measure each of the phase currents. So we got the 4 wires. Then we're going to use 3 wattmeters to measure the total power. So this is what goes on inside the instrument. So on a 3-phase 3-wire system, Blondell says we only need 2 wattmeters. So we'll hook up, one of our wattmeters. And you really need to follow the wiring diagrams that are in the manual, if it's Yokogawa or if it's some other manufacturers. Follow the wiring diagrams, but we're going to put a wattmeter in 2 of the lines. We're going to measure the current, and we're going to measure the voltage line to line. And this is a typical way that we would wire up one of the Yokogawa power meters with a 2-wattmeter method. And then the total power is just going to be the sum of these 2 readings. Now, these could be 2 individual indicating wattmeters, or they could be what we'll call a 2-element 2-wattmeter power analyzer that's going to total it up for you. So the advantages of a 2-wattmeter system: it's a simple installation, simplifies the wiring configuration. Because if you're using current transformers, you only need to use 2 of them, and potential transformers, you only need 2 of the potential transformers, so it can cut down some of your cost. And so this is an accurate power measurement on either a balanced or an unbalanced system. So we are making accurate power measurements. And so it's a good system for production testing. Your design's done. You know what the system is. You just need to measure the total power. And so it's a simple, easy to install system. Now we provide a Another wiring configuration in the Yokogawa power analyzers is what we call the 3 voltage 3 current method, 3V3A, for a 3-phase 3-wire system. And in this case, we install all 3 watt meters. So we look at all 3 voltages and all 3 currents. And this is a 3 watt meter. Now power is still going to be calculated from just the 2 watt meter method, but this provides the way of looking at all 3 voltages and all 3 currents. And I say this is the best method for your engineering and R&D work. You need to know what each one of those voltages are. You need to know what each one of the currents are, so you can do any balancing or any design work that needs to be done. A little bit on power factor. For a sine wave and a sine wave only, we refer to power factor as the cosine of theta, or the cosine of the angle between the voltage and the current. This is defined as the displacement power factor. It's the displacement in degrees between voltage and current. And this is what our power utilities typically look at for, when we talk about power factor, as the cosine of the angle, displacement power factor. But for all other waveforms, distorted waveforms and things like that, true power factor is calculated as the watts divided by the VA. So it would be, for a polyphase system, total watts divided by total VA. So using a 2 watt meter method, or wattage, okay, it's going to be a 2 watt meter method for watts, and then we're going to look at the total VA. So total watts is just, say, watts 1 plus watts 2, the 2 watt meter method. And then the VA, we're only looking at 2 of the VAs, the volt amps. So we look at VA1 and VA2. Okay, we multiply by the square root of 3 because it's a line-to-line measurement. We divide by 2 to get the average of the VA. If the load is unbalanced, say the currents are different, okay, in each one of the phases, this could give you an error in your calculation, because we're assuming when we divide by 2, we're making an average based that the VAs are equal. And so if they're not, if they're unbalanced, that could give us an error in that power factor calculation. The VA calculation is going to be, the total VA is going to be slightly off. Using the 3 watt meter method, the 3V3A method, so we look at total watts, which still, again, is a 2 watt meter method, watt 1 plus watt 2. Now we're going to look at all 3 of the VAs. If they're unbalanced, they're going to be in our equation. All right, so we're looking at all 3 VAs. We take the average, divide by 3, and we still got that square root of 3 because it's a line-to-line measurement. So this is the best method to use either on a balanced or an unbalanced system, especially when you're doing your engineering work. And in our power analyzers, Yokogawa power analyzers, it's what we call the 3V3A wiring method for a 3-phase 3-wire system. So again, we recommend using, for your engineering work, the 3V3A wiring method. Gives you the most accurate method for power factor and for VA measurements, either on a balanced or an unbalanced 3-wire system. Okay, let's look at some mechanical power measurements now. In an electric motor, the mechanical power is basically just speed times torque. And the mechanical power typically is defined in kilowatts or maybe horsepower. Now, 1 watt is a joule per second, or also a Newton meter per second by definition. So mechanical power then is 2 pi times the rotating speed divided by 60 times the torque. And the rotating speed is in RPM, revolutions per minute. And torque, the basic torque measurement, is Newton meters. This will give us mechanical power in watts. So horsepower is the work done per unit of time. 1 horsepower is going to be equal to 33,000 pound-feet of work per minute. Or we can convert that to horsepower equals to the RPM times the torque in pound-feet divided by a constant 5,252. Now, often you'll see the conversion of horsepower to watts. You might see those in a simple term, 1 horsepower equals 746 watts. Okay, that's a quick conversion to give you an idea, horsepower to wattage. The actual number, when it all calculates out, is 745.69987 watts. So we got all these decimal points in here. So, like I say, you'll may see some variation up here of maybe 745.7 or 746 as the conversion of horsepower to watts. In an AC induction motor, the actual speed, that's the speed at which the shaft rotates. And this is typically measured with a tachometer, some type of a tachometer. Now, the synchronous speed, that's the speed of the stator's magnetic field rotation. And this is the motor's theoretical speed because the rotor always turns slightly slower. So we can calculate the synchronous speed as 120 times the frequency divided by the number of poles. And this will give us what we call the synchronous speed. Now, we also have the function of slip. That's the difference in the speed of the rotor, which I call RS, for rotor speed, and the synchronous speed, which I just call SS. So percent of slip, then, is just the synchronous speed minus the rotor speed divided by the synchronous speed. And these are all functions that we'll look at in the motor operation. Now, efficiency in a basic, simple form can be calculated as the output power to the total input power. So the output power on our motor is what we call the mechanical power, P sub N. And the input power, then that's just the electrical input power to the motor. Let's look at some instrument selections now. Here's a few standards that we have in North America, the IEEE 112, NAVLAP 150, and the CSA C390. These are specifications from these standards that specify the accuracy required for the measurement. So the power on the IEEE is defined that we need to measure that with an accuracy of 0.2% of full scale. Voltage and current, also defined as 0.2% of full scale. And most of these follow along about the same. Now you'll see the CSA says 0.5, but that includes CT and PT errors. With the IEEE and NAVLAP, they bring out the CT and PT separately as 0.3% of full scale, and that's the ratio and the phase error. Then torque needs to be measured at 0.2% of full scale. CSA defines it a little bit different as 0.7% of reading. Okay, so that is calculated a little different. And so the motor speed and RPM, all of them within 1 RPM. Then there's also some temperature and resistance winding accuracies. But as far as the electrical part of it, this is what we're looking at up here. So it gives you an idea of what type of instrumentation that we need to use. Current sensors. Generally, on the power analyzers, we're limited to low current input, maybe in the 30, some of them go up to 50 amp input. So most of the time, we have to use some type of a current sensor. And we provide a lot of different current sensors to help you with your installation. Here's some that we work as a reseller for AEMC to make some nice clamp arms. And we have selected some of these clamp arms that are best for power measurement and best for accuracy. Now, usually these clamp arms are not going to meet the IEEE 112 or the CSA type specs. Their accuracy on the clamp when you split the core just isn't that good. Scope probes, usually small scope probe. You have to be careful of those. Yokogawa in one of our business units. We do manufacture some very good instrument current transformers with good high accuracy, very low phase shift, and very high current up to 1,500 amps. So we do have those to offer. For our DC measurements, we want to use a shunt, DC shunt, and we resell shunts made by RAM Meter. And Pearson Electronics makes some good high-frequency CTs, but again, their accuracy for the motor testing standards probably is not good enough, but they are good for real high frequency. And then we have a special system that we have put together based on the Dan-Physic, which is LAM Dan-Physic CTs now. These are an active type transformer. Very good system, operate from DC up into the high frequency, hundreds of kilohertz. Very good accuracy, accuracy in the basically 0.05 to 0.02% of full scale. And so it's a very good system for DC to high frequency, especially when you're using this with a variable speed drive. So we have a lot of solutions that we can help you with your current sensors. Things to consider when you're working on selecting a current transducer: frequency range. If you're going DC to line frequency, if it's a sine wave, you can use a shunt. If it's much higher than line frequency or distorted, those types of bus bar shunts will not work. If you're doing DC and AC, then you can use something like what they call a Hall effect sensor, or like the LAM Dan-Physic, which is an active type of a current transformer. A normal instrument transformer will typically operate from about 30 hertz and higher. So if you have to go down to low frequencies, then we have to look at some other type of current sensor. The accuracy of a current transformer typically is defined as the CT turns ratio. Another important thing to look at is the phase shift of the current transformer. Some inexpensive current transformers are made just for current measurement, and so they're not corrected for phase shift if you're just reading amps. But when we're reading the power, then the phase shift becomes a function of the power factor. So how much phase shift can you withstand? Depends on your application. If we had 2 degrees, that's a 0.9994 cosine of 2 degrees, or 0.06% error. We may need to do better than that. Again, so we have a lot of solutions that we can offer you. The instrument compatibility, we have to look, well, what's the output of that transformer? How's it going to connect to the power analyzer? We may have outputs on some of them that are in millivolts per amp or milliamps per amp, or standard instrument transformer typically may have a 5 amp output. The impedance, the load, we call burden. How far away is the CT from the instrument? How much is the impedance of the instrument? Lead length, all this adds up, so it has to be taken into consideration if you have long lead runs. Scope probes, I say caution on this. A lot of scope probes will not match up with a power analyzer input. They're made for a scope input with an impedance and capacitance that's typically on the front end of the scope. So we have to be careful with some of these scope probes. So that's where I say a word of caution, be careful what we're doing there, and make sure that they are compatible with the input characteristics of the power analyzer. And then, of course, finally, we have the physical requirements such as size, connections. Do we need a clamp arm or a donut type? And then, again, this distance from the load to the instrument. Let's look at electrical power measurements now on our three-phase AC motor. So we've got our motor. We're going to look at the three-phase input to the motor. This is a screenshot from one of the Yokogawa power analyzers. Their functions can be changed the way we read it, but this is just a typical readings that you might set up. We can look at all 3 voltages, look at all 3 currents. So I had 120 volts on each line to line. I had, this was a small load, 415 milliamps on each phase. You can see they're pretty well balanced. Total power, in this example was a little over 77 watts, and then my power factor was running at 0.89912. So you just, on our units, to set up your display to see what you want, and in any type of format. Now, on the three-phase, three-wire system, remember, we only need to do the 2-watt meter method, even though we can display all three. And here's what happens if you're looking at all three of them. Here's one of them. One of the input elements is reading about 18. This is reading about 4.9, almost 5 watts. Here's a little over 13 watts. But the total power, okay, this is P1, P2, P3. Total power, which is displayed as P and then sigma or total in a group A, just the way our units work. It's the sum of P1 and P2. So these two added together will give us the total power, 22.978. So on a three-phase, three-wire system, you cannot measure the phase parameters. You cannot measure phase watts, phase power factor, okay, because remember, power factor is watts divided by VA, so we don't have phase watts. That's just the laws of the physics of the three-wire system. So we can look at the three voltages, the three currents, okay. This is the total VA, total VAR, and here's my total power factor in this example. So on a three-phase, three-wire system, if we look at the waveforms, we'll see that the waveforms are connected line to line, and the way the instrumentation sees it, these voltages are 60 degrees apart. They are not the phase voltages. We do see phase current, so these are nice, balanced 120 degrees apart. So here's what's happening. If we think about our phase as the red lines here, this would be our typical line to neutral measurement, and we would see the voltages 120 degrees apart. This is what we would expect to see. That's the way they're generated from the power utility and balanced 120 degrees apart. But the voltages are not connected line to neutral. They're connected line to line. So in this example, the meter is hooked up, and this is the way the meter sees voltages. They're hooked up to read voltage as this voltage here A to B, and this voltage B to C, this voltage A to C. Okay, so now the voltage vectors are in a triangle, and if it's balanced here, these voltages will be 60 degrees apart, not 120. Now, I've just thrown in my current to the blue line here at some arbitrary value. And if these currents now become, phase shift becomes 0, so they would be on top of the red line here, you can see that the currents now, there's an additional 30-degree phase shift, the way the meter sees it, between voltage and current. So that's what's happening inside the power analyzer. So it's kind of complicated, and a lot of times it's not what we expect to see, but that's what's happening because the meter sees these things out of phase with each other, and then it has to make the proper calculations. Actually, sometimes if the meter's not corrected, we could see one of the phases or one of the elements, especially on some of the older instruments, as actually being a negative watts. So if you had one of the older instruments, you might see one of the elements that's not used as negative watts, but the other two should be positive. We have a function that we call a delta measurement that if you're hooked up in the traditional line-to-line, you may want to know what the actual line-to-neutral values are. And so this is a math calculation that we use. It's not just a square root of 3 calculation. It's a true digitized value. So if they are unbalanced, we are looking at the actual digitized values and the phase relations to get these calculations correct. So it's a amplitude vector calculation to make true delta measurements. So this would give you the equivalent line to neutral voltage measurement based on the measured line to line. And with this also, we can calculate any neutral current that might be flowing. So those are some other functions that are available that we can do in the power analyzers. So, the question is, what if you need to measure the phase power and the phase power factor on your three-phase, three-wire motor? Well, here's a little undocumented tip. You won't find it in the manuals because there's a lot of conditional functions that can happen here, so you have to be careful. We can create what is called a floating neutral on a three-phase, three-wire system. And we put the power analyzer into a three-phase, four-wire measurement mode, and we create a floating neutral across the low side of each of the voltages. So see how we connect the low side of each of the voltages together. Okay, and this becomes a floating neutral for voltage. It doesn't go anyplace. It's not grounded. It just stays floating. And then we put the instrument into a three-phase, four-wire measurement mode. And this is the equivalent of measuring then a line to a neutral voltage measurement. And we may or may not have CTs in there, but that's in the other part of the circuit. This is just the voltage side that we're talking about. But here's my point of caution. This will work on a motor without problems if you have a regular induction motor, synchronous motor, or similar type without a variable speed drive. If you have any type of variable speed drive, the high frequency, the sorted waveforms, the harmonics will cause some inconsistent measurements and will not work because we're actually getting some circulating current through that floating neutral. So if you're just looking at a motor, sine wave input, this technique will work. So I just want to repeat a caution. Use this technique only on the products with sine wave type inputs. Now I say, well, I got a variable speed drive. Okay, there's one other thing we can do. We can get rid of all that high frequency if we turn on the line filter, or which is a low-pass filter. And in ours we have a 500 hertz low-pass filter. It's just going to filter out the way the instrument would see it, all of the high-frequency components. And then it's basically looking at what we call the fundamental voltage and current, filters it out back to a sine wave, and then you can see the phase parameters. But there's a lot of things you have to be careful with. That's why it's not covered in the manual, because there's too many things of areas. To get into this, have questions, you can give us a call. So if we look at the three-phase, three-wire versus a three-phase, four-wire, remember on the three-wire system, the voltages are 60 degrees apart, and we're looking at phase currents. On the four-wire system, we are looking at true phase voltages and phase currents. Now the power in the device, it's going to be the same whether we measure it as a three-phase, three-wire or as a three-phase, four-wire system. The device is drawing the same power. It's just the way we measure it. So here's some typical measurements. I did this with one of our six-element power analyzers. Hooked up three of them on a three-phase, three-wire connection. Hooked up this side with a floating neutral three-phase, four-wire connection. Okay, and down here you see the power. Both of them reading 40.87, 40.89 watts. Power is basically the same. Power factor is basically the same. You'll see the voltages. You'll see the phase currents are the same. And the voltage line to neutral times the square root of 3 equals the line-to-line voltage. Okay. So just a calculation check. We did pick this one right here, 55.2 times square root of 3 gives us the 95.6. So the math works the same as the measurement. Let's look at some mechanical power measurements now on our AC motor. So we've measured the input to the motor. Now we'll look at the speed and torque of the mechanical measurements. There's a lot of manufacturers of speed and torque sensors. A few of them that we've worked with. There's probably others, but Honeywell, Central Tech, or Lebo is now part of Honeywell. Himmelstein, Magtrol, HBM, and like I said, there's probably some others, but these are some of the most common ones. So in selecting your sensors, there's a lot of different types of sensors, there's different sizes. There's a lot to it, and I recommend that you work directly with the sensor manufacturer for the selection for your application. They're the experts, and directly work with them. Just looking at a few of them here from Himmelstein, they got some inline digital torque meters. There's another one off their website. Most of the manufacturers will provide some type of a signal conditioning unit readout so that you can read the instrumentation, speed, and torque directly. And these are matched for their sensors with all the correct signal conditioning. Here's some stuff from Honeywell. They have a large selection of different types of sensors. And again, they have their own signal conditioning unit. Here's some stuff from Magtrol with their inline speed and torque sensors. They make some test benches that you can build up your own test system with your brake and your speed and torque sensor. And this is their electronic controller for the dynamometer, for the brake, for the speed and torque sensors, the signal conditioning unit. So how do we do the mechanical power measurements? This is what I just call system number 1 for the seminar here. We're going to use the sensor, the instrumentation from the sensor manufacturer. We have a speed sensor and a torque sensor. We're going to use their instrumentation for this signal conditioning. And this output then could go to, this device right here could give you some type of the digital readout for speed and torque, maybe mechanical power. Could give you an output to the PC, and then application software that's maybe provided by the sensor manufacturer. But this just uses all the sensor manufacturer's equipment. Here's a small system we use here based on a Magtrol system. We got their speed and torque sensor here in the middle. We've got a brake for a load right here. This is the Magtrol controller that provides signal conditioning to the speed and torque sensor, controls the brake, will give us a digital readout. It'll provide the output to other instrumentation if you want it. Here's the motor back here. This is a Novatorque motor, and it's actually one of their systems that we use as one of our test fixtures also. And then there's a little motor drive back here in the back. But that's a complete small system for a small motor. So the advantages of what I call system number 1, we're using the matched system for the sensors from the sensor manufacturer. It's going to provide all the proper signal conditioning. Usually give us some readout in torque, speed, and power, mechanical power. Could provide a communication output like an RS-232 or a GPIB. And it might also give us an analog output for other readout instruments. The sensor manufacturer may have their own application software. And again, I recommend working directly with the sensor manufacturer on this. Now, for what I call system number 2, we're going to do the same thing. We're going to use the sensor manufacturer signal conditioner. We've got the speed and torque sensor. Now, we're going to take the speed signal and a torque signal from the signal conditioner of the manufacturer and feed it into some of our power analyzers that have a separate input for speed and torque. Now, the power analyzer now is going to calculate the mechanical power based on the speed and torque. And from the power analyzer, then, we can go to a PC and an overall application software. Now, this could be a complete specialized custom software package. Could be a generic software package, just from the power analyzer. But we got the whole system now being measured with the power analyzer. So the advantages of this system, again, we're using the sensor manufacturer's signal conditioning. So we're matching the system to the sensors. They're going to provide the proper signal conditioning and an output to the power analyzer. Okay, so now the speed and torque signals, conditioned speed and torque signals are provided to the power analyzer. And the power analyzer now is going to calculate both the electrical power from the motor and the mechanical power. The advantage here is both electrical and mechanical power are going to be calculated simultaneously. So there's not going to be any skew in the measurements. We're going to have the best and most accurate efficiency calculations this way. Then we can use some type of custom or generic application software to measure the whole thing. In the power analyzers with a what we call a motor input, we have the ability to bring in the signal for speed and signal for torque and do all the scaling. For speed, we can typically bring in, this shows the analog voltage, we can bring in analog voltage or a pulse input, pulses per revolution. The same thing on the torque, typically that's an analog voltage input. And we just set the voltage ranges to match the sensor. Okay, the output from the signal conditioning units. And then here we can, if we are using a pulse sensor type here, we can set the pulses per revolution. So this is just an example of showing 60 pulses per revolution instead of the analog voltage input up here. So you just choose one or the other. A little bit earlier, we talked about the synchronous speed. Here's where we can select the synchronous speed based on the number of poles, and then that'll be a parameter that we can read out. Then on the front display, you can set your display up to read speed. Here we're reading 3,600 RPM, and the torque, in this example, 5.26 Newton meters. Now let's look at some PWM or variable frequency drive measurements with our AC motor. So we got our drive. We're going to look at the input and the output of this drive. The output of the drive then goes into the motor. And this is done with one of our 6-phase power analyzers where we can look at 3-phase in and 3-phase out. Now this input to the inverter could be a DC input, could be a single-phase AC input, or it could be a 3-phase AC input. We're just showing a 3-phase AC input right now. Here's another one of our variable speed drive trainers that we use. This is a PWM motor drive that brings a single-phase AC in. I got my 3-phase AC out, voltage and current. It's a small system, only draws a few amps. And we got a bunch of taps that we can look at various parts of the signal. But this drive then is running this induction motor. And this induction motor is hooked to a blower, and it just uses some type of a load here to put a little bit of a load on that small little motor. But it is a PWM type of a drive, and so this is one of our trainers. And a lot of the screenshots that you saw were developed off of this trainer system. So here's our PWM voltage. It's a chopped square wave. We've got some noise up here in the voltage. You got your high frequency switching. And then we'll see the current. The current is, basically there's a sine wave in there. The motor works as a, it's an inductor, so it's a filter. But there is some, a lot of noise still on that. There's not a whole lot of energy in there, but there is still a lot of noise on there. There are harmonics, of course, on the current. A lot of harmonics up here on the voltage. So issues in measuring our PWM drive, we got high frequency switching on the voltage signal. And so depending on your drive, your technology, these can be switching frequencies up into the kilohertz. The variable frequency of the drive, the advantage of that, it can start at 0 hertz or, where it's not moving, and go on up in frequency to the operating speed of the motor. And on the current side, again, we have a lot of noise on the signal. And again, we still have to measure that current from the 0 hertz with your drive on up to its operating speed. And so we have distorted waveforms and a little bit lower level harmonic content, but there still is a harmonic content we have to look at on the current side. So this is going to take a very accurate power analyzer to make these power measurements with a wide bandwidth power measurement capability. Looking at what we're talking about, the harmonic spectrum. Here's that harmonic spectrum of that PWM. You can see some beat frequencies that are in there. This went out to, it goes out to in excess of 500 orders. This particular instrument went to 500 orders. You can see the 500 there. That was basically 30 kilohertz on a 60 hertz fundamental. So again, we have a lot of high frequency. Now on the current side, you can see a couple little spikes there. This is a log scale, so they're not real high. There's not a whole lot of energy. They roll off pretty quick down here in the low frequency from the fundamental side. So, how do we make the measurements? Inverter voltage measurement can be made two ways. One, we could look at the true RMS measurement, and that's going to include all of the harmonic content. It'll give you a very high reading. Typically, we want to look at the fundamental amplitude. That's the amplitude of the fundamental wave, and that's what basically contributes to the motor torque. And the frequency, of course, is going to be a variable frequency from 0 hertz on up. And then the current is typically measured one way. It's measured as RMS only. So we want to look at all the harmonic content, and the RMS value is what's responsible for temperature rise within the motor. So we want to look at RMS current and typically the fundamental voltage. So how do we measure the amplitude of that fundamental wave? Well, one way we can just apply, this is what we used to have to do on instruments, was apply a low-pass filter. And that'll give us the filter down to the fundamental if we have the proper filter frequency. Just filter it right down to the fundamental. But it's also going to filter the current, and it's going to filter the power measurements. Basically, I say filtering is not desirable. That's an old technique. We don't need to do it that way anymore. The other way is using what we call a rectified mean measurement method. This algorithm will give us an RMS voltage of the fundamental without filtering. And it uses a mean value voltage detection scaled to RMS. And it's going to be very close to the true RMS of that fundamental wave. And it's been an accepted method, this algorithm, for many, many years. So here's what we're talking about. If we know the RMS value, and say we want to get the peak, remember that's square root of 2, 1.414. This average, half-cycle average, or mean, okay, this is the way the old analog meters used to work, and they had a scale that was given the RMS value. So if we get the average, half-cycle average, put a multiplier of 1.11, that would give us the RMS value. And so this is the function that we're using with this average or mean algorithm. The other way we can do it is a harmonic analysis to truly to determine the true fundamental. We can use the FFT, fast Fourier transform, to break down the waveform and get the true fundamental. It's going to give us an accurate RMS value of that fundamental wave. And some of the new power analyzers can make these measurements of harmonics and the normal power measurements all simultaneously in the harmonics mode. So here's an example of one of our screenshots. Here's the PWM. This is the input side, so we're not going to look at that. This is the output side. We're going to look at one of the voltages. The RMS value of that PWM was 219. This is a math function where we determined the mean value, scaled to RMS, 194.342. This is the filtered method. Now I did it over on another element, okay, because I can't filter the same channel. So I turned the filter on channel 3. You can see that low-pass filter, basically about the same, 194.669. This is done with the harmonic, okay, and this is done on channel 2. So we take this RMS value, do the FFT harmonic analysis on channel 2, and 1 indicates that that is the fundamental frequency, and that's 193.8. I would say this is the most accurate reading right here, but all of them, either three methods, are all very close to get that fundamental voltage. So let's look at efficiency measurements on your drive. Drive efficiency is basically calculated, as output power divided by the input power, and expressed as a percentage. Now, we can use 2 power meters to measure input and output power, and then calculate the efficiency. But here's the problem by using 2 meters, that we may not be getting the data at exactly the same time, and so we've got a possible skew in our data. There's a time skew and a possible error that way. So this is why we like to use the multiple element power analyzers to measure both the input and output simultaneously, and then calculate the efficiency inside the single instrument. And this is going to eliminate any time skew and error. In some of our power analyzers, we have the math functions to very simply set up the equations for these efficiency calculations. And here's an example of a drive efficiency. This is on our trainer where we had a single-phase input and a 3-phase output. So my 3-phase output is this sigma of all 3 elements, the P sigma A is what we call it. And P4, that's our single-phase input. And then times 100%, so we get the efficiency in percent, and we use the symbol N eta for efficiency. And we got, in this particular unit, we got 4 equations that we can set up very simply. So in addition to drive efficiency, maybe we want to look at the drive power loss. Okay, sometimes we want to actually know what our losses are inside. And we can do this. We have some user-defined math functions inside some of our power analyzer that would let you do this. And we just write an equation internally as the input power minus the output power. Here's an example again of a screenshot. This was the output power, the 3-phase output power, 30.8. This was the single-phase input power, 54.987. I can calculate the efficiency is running at 56%, and I had 24 watt loss inside, which is just the difference between these two. Now this drive was running pretty slow, that's why it's pretty inefficient. It's running at 20 hertz. Lightly loaded. The other thing that you may want to measure is the volts-per-hertz. A drive should maintain a constant volts-per-hertz ratio over its operating speed. So we can verify this volts-per-hertz ratio within the system. And again, we just set up a user-defined math function to do this. Here's one of the math fields, and we can calculate this either on the RMS voltage or the fundamental voltage. The ratio is what we're looking at, that it's constant. So we could write an equation we're going to get the voltage on this case, it's element number 1, and divide it by the frequency that we're measuring, again, on element number 1. And this was the RMS value. Here was the fundamental value. So it says order 1 for my voltage. And then we divide by the frequency again on element number 1. So they're easy math function setups within inside the instrument. Here's the display of our Volts-Per-Hertz. Here's the math function based on the RMS value. Okay, so the voltage is going to be higher. Okay, and then this is based on the fundamental. Sometimes we may want to see, what that DC bus is on our PWM, and we may not be able to get into the actual drive to measure that. So one of the ways that we can do it a little bit different is to go back and display the waveform. And here's our PWM waveform. We can expand that out so we can get an idea of this top value here. Now you want to be careful that you don't pick up any of the peaks, the spikes. There's a little white cursor that I've laid out right across the top there. Okay, and then I've done a cursor measurement. And here, laying that cursor right up there, I can see I got 302.81 volts as my DC bus voltage using the cursor measurement. So here's a way that we can get a pretty good idea of what that DC bus voltage is without having to get totally inside the drive, which may be inaccessible in certain applications. So as a review, some of the setup modes, if you're using our power analyzers, it might be similar if you're using some other type of power analyzer. But if you're using our power analyzer, say on a WT1600 or a PZ4000, we want to measure what we call the normal mode, okay? Not the harmonics mode, but the normal mode. Normal power measurement mode, where you see all the RMS values, you get the mean values and everything like that. In the WT3000, now that operates a little bit different because it does the normal mode and the harmonics mode all simultaneously. So what we want to do is what's called on that one is the RMS mode. We're going to measure all the RMS values. Wiring configuration. Typically, I suggest you use the 3V, 3A, 3 voltage, 3 current connection. Look at all 3 voltages and all 3 currents. The best system, especially if there's any possibility of being unbalanced. Filters, typically we want the line filter or low-pass filter off. We do not want to filter our measurements. Generally, we can turn on what we call a zero-cross filter or a frequency filter. This way, it'll cut out that high-frequency noise. It will not filter the measurements because they're parallel circuits, and this will give you an accurate frequency measurement of your drive and motor. Voltage measurements on the WT1600 and PZ4000 use the mean voltage measurement function. You could switch over and use the harmonics, but then you have to switch back and forth between the modes. So typically we just set up the mean voltage measurement. On the WT3000, we can use the math function and get the mean, or if you have the harmonics option that runs simultaneously, you can look at the U, say the element number 1, which is order 1 or the fundamental. So WT3000 has some newer functions that run the harmonics simultaneously. All right, kind of wrap it up here, looking at the total system. We're going to look at the total system. Here's a big custom motor test stand system, the motor and the load and the instrumentation over here. So now we're going to look at the three-step process. We're going to look at the input to the drive, output to the drive, which goes into the motor, and look at the mechanical power. So we can make the accurate measurements of the PWM variable speed motor, which is the drive input and output power. We calculate the drive efficiency and the power loss. We showed you how to do that in each individual step. Then we can make the other drive performance functions, power loss, Volts-Per-Hertz, and things like that. Then we can look at the aggregate measurements of the input power to the motor. Look at the electrical performance of the motor, the efficiency of the motor. Look at the kilowatts, the horsepower, the power factor. Then we can look at the mechanical power. Okay, these are measured speed and torque. Calculate the mechanical power. And we can calculate speed-torque curves and look at the overall efficiency. All this we can do with the power analyzer. All electrical and mechanical power measurements can be done simultaneously, and this is the important part, inside the power analyzer. So there's no time skew between the errors, between the measurements, so there's no errors in your calculations. Then it can be used with a single, custom, or generic software solution. Here's the motor test system. Again, doing the calculations. This is where we did earlier the drive efficiency. This was a three-phase out and then the single-phase in. But it could be a three-phase in. We just changed this input symbol right there. So there's your drive efficiency. This is what we call method A, motor efficiency, mechanical power divided by the input power to the motor. And here's our total system efficiency, from the mechanical power to the single-phase input to the drive. So you can see how we can calculate all those parameters simultaneously inside the instrument. A little bit on IEEE Standard 112. This is the standard test procedures for polyphase induction motors and generators. And it defines all the parameters such as, everything inside the motor, the electrical, mechanical test, the temperature, resistance test, efficiency test methods, all within this standard. Very comprehensive, very detailed standard. Test method A, very simple, is an input-output method defined in the IEEE 112. So that's basically the mechanical power divided by the electrical input power. Very simple. Test method A. The one that we see more often for the motor manufacturers is what they call test method B. And this is input and output with all your other losses calculated input. These typical losses are the friction, I2R losses, other stray load losses, core losses. A lot of the losses within the motor are taken into account in this, so it takes a lot more instrumentation. It's a very much more detailed type of a test, and it would give you a much more accurate or actual type of a efficiency calculation with all these losses. And there's other tests that are defined in there, and which method should you use. Kind of the thing here, if you're an electrical motor manufacturer, use method A or B. Method B with your losses is pretty typical in that industry. The easiest way for us to do it is the method A, which is just looking at the mechanical power and the electrical power input to the motor. But that's some things you will have to, really determine as to which method that you need to do for your particular application. So to kind of wrap things up, what we're trying to do is give you real quickly here a three-step process for our complete test. We've reviewed the basic electrical power measurements, looked at the mechanical power measurements, talked about different instruments and current sensors to use for the motor testing. Got into the three-phase AC motor measurements and especially the peculiar things that are with a three-phase, three-wire system. Looked at some of the solutions with the speed and torque sensors, looking at motor efficiency measurements. Covered some of the things on a variable speed drive, such as the input and output electrical measurements. things that you need to be aware of on the drive, how to make those correctly. Look at your drive power loss and your drive efficiency, and then some other drive measurements such as the losses and volts-per-hertz. Try to put it all together for you as a complete system and show you how that we can do all of the measurements with one test instrument to solve your engineering and your testing work. Hopefully we've answered questions. We're at a full 1 hour here. I think there may be a few questions. We'll probably try to answer those on an email basis. And so again, if you do have questions, we do want you to submit them. Thank you for attending. And with that, I'm going to turn it back to Sophia for a little bit of the wrap-up. Again, thank you very much. Bye-bye.
Thank you, Bill, for a wonderful presentation. We have run out of time for a Q&A section. Please be assured that if you submitted questions, they will be answered via email. With that, I would like to once again thank you all for attending and participating in this online web seminar. Also, if you have not yet answered the poll questions, I would request you to please do so at this time. I would also like to mention that this seminar was recorded and will be available for replaying in archive form 24 to 48 hours under the technical library of our webpage. I will be sending everyone a link when it is up for your viewing. Thank you once again, and we hope to see you online at our future web seminars.